Hello everyone, welcome back. Today I'm going to provide you with another full explanations on further mechanics, the Cambridge CIE paper. The syllabus code is 9231, right? So specimen paper, paper 3, right? You can check out the description here, right? Now I hope that it will be useful for your uh, upcoming exam, right? Let's get started. All right, welcome back. Let's take a look at the first question of this specimen paper, paper 3. Right. So a child's toy consists of a uniform solid circular cone. You can see that from the diagram on the right hand side. It has a vertical height of 3r. So just let me label that any information is given 3r. So it has a vertical height of 3r here. Okay, and then a radius r, so it has a radius of r here. Okay, and a uniform solid hemisphere of radius r also, which are attached together with the cone, okay, to form a composite rigid body here. Now the cone and the hemisphere are made of the same material, which mean they both have the same density. Let's call the density for this material as rho. Um, Now let me get one thing straight. When I refer to density, I'm actually talking about the mass density, because as you further your uh, study in either mechanics or physics, there are many different measurements for density. So one of them is mass density. So we are talking about the its mass density in this case, right? Okay, now our task here is very simple. Just to show that the center of mass of the toy is at 27 over 10, or which is 2.7 r from the vertex of the cone. So the vertex of the cone would be somewhere here. All right. Okay, now there's one more label I need to make here just to make sure we are clear. The height of this hemisphere would also be r. Okay, so I hope that is clear at this point. Right, now do read through the question in the exam. Read through it thoroughly before you even start to answer it. Right, and then diagram is vital visual representations that I always find it very useful. So always draw your diagram, represent all the informations that are given to us. Okay. Now in this case, I have also added an axis, or sometimes you can say that frame of reference to this cone and the hemisphere composite rigid body here. Right. Now, because the measurements of the center of mass is with respect to the vertex of the cone, so that's the reason why I set up my x and y Cartesian coordinates to start from the origin at the vertex of the cone itself, right? So you can see that we start off from here. Right? So you can put your reference frame any way you like. Okay, but I find that for these questions, the reference frame would be best put here. Okay, so I hope that is clear. Just check through if you have all the informations there, right? If you are happy with that, okay, then we are going to set up a table also, a table that consists of all the informations that we need for us to apply the principle of moment later. Okay. Now the informations that we need usually are the volume, because we are talking about a solid body here, so we need to know its volume. Now we can find out its mass by using a general representations of the mass density, and then we can find out its center of mass also at this point. Okay, right. Okay, now let's start with the cone itself. The volume, if you can't remember the volume for the cone, you can always refer to your MF19 in this case. Okay, now for the volume of cone, it will be 1/3 pi r square, and then of course multiply by its height, which is 3r in this case. Now of course you can simplify this as it's quite direct from here. You can see that is pi r cube, right? And then for the mass itself, okay, for the mass itself, we know that from the formula of density. Density is given by mass over volume. Now we have our volume here. We are interested to obtain the mass itself. So therefore, yeah, maybe here I'm gonna label this as volume. This is mass here. Okay. So therefore, in this case, you can see that the mass is basically density multiplied by volume. Here we are quite lucky because both of these material are made of the um, same compound, I would say, or same elements. So therefore, they should have the same density in this case. Right? Okay. For that, we're going to write down our mass as rho pi r cube. Now that will be our mass for the cone. And then the center of mass for the cone. Now, you can refer to the MF19. Okay, now we'll show you your MF19 now. Okay, if you scroll down and then check out these sections here, especially, yep, you will be able to identify the conditions or the setting for the center of mass for any sort of rigid body that may come out in your exam paper, right? So here we are interested in the solid cone itself, so we refer to this section. All right. Okay, if you are clear, we're going to take this back to this section here. So you can see that the center of mass is actually located at 3/4 measured from the vertex itself. So 3/4 from here. Okay, so 3/4 from here. That will be 3/4 from its vertical height. So here we have the vertical height, which would give us 9/4r. All right. Now I hope that is clear at this point. Now next, we're going to move on with hemisphere. Hemisphere, the volume of hemisphere is quite clear. Is 2/3 pi r cube, of course. All right. And then there you have it. And then the density for the hemisphere is the same as the cone. So therefore here we can write it down as right. And then the center of mass of hemisphere. All right, let's go back to the MF19 again. We are going to refer to the same section again. Now you can see that the center of mass of hemisphere measured from the center of the hemisphere. It is located at 3/8. 3/8 from the center of the hemisphere. So, all right, now let's bring this information back. So it's 3/8 measured from the center of the hemisphere, right? 3/8 r the radius. So we'll just write down 3/8 r. All right, which is 3/8 r, and then don't forget the center of mass of the hemisphere is measured from the vertex itself. Okay, so therefore the distance of the center of mass of the hemisphere with respect to the vertex is given by such 3/8 r plus the 3r there. So I hope that is clear. Always refer back to your frame of reference in this case. So therefore 3R, and then that would actually give us 27 over 8R. All right, and then there you have it. And then all we need to do is complete the composite body section here. All right, now we know that the volume, now in this case, let me rewrite this again. This volume is pi r cube. Okay, so from here, we will be able to deduce that the composite body's volume will be 5 over 3 pi r cube here, and then the mass itself will be 5 over 3 pi r cube, and then we have no idea where is the locations for the center of mass for the composite body. So here I'm going to label that as a y bar. All right, now assuming that the location or the distance of the center of mass of the composite body is located somewhere here, for instance. And then do pay attention to the reference frame. So I'm measuring my center of mass for the composite body with respect to the vertex here. Okay, so this is what we would expect to get for our center of mass here, right? So by using principle of moment, we know that the sum of all its individual rigid bodies component, the sum of moment for all the individuals rigid bodies component would be the same as its moment for the composite body. In this case, I will label that as M, where in this case the mass for the composite body is actually given as such. So just a reference here. So I'll write down as, all right. So this is the mass. This is the volume section, right? Now, what is left for us to do is very direct. All we need to do is just substitute all the informations that we have at this point of time. So, therefore, for the first rigid body component, the cone itself, so we take the mass, multiply with its center of mass with respect to the vertex itself. Now, therefore, that would be, I'm going to simplify that directly so that it's easier for us. Now, in this case, we will have 9 over 4 rho pi r to the power of 4 here. And then that will be the same as 5 over 3. All right. Okay, now this is given as such. And then we need to add up the moment for the hemisphere. Now, in this case, if I try to simplify that, I would get like 9 over 4 also. All right, so there you have it. And then from here onwards, we can simplify it further. So that will be like 9 over 2 in this case. Okay, and then by simplifying that, we will be able to reach these conclusions, 27 over 10 R. Therefore, we have successfully proven that the distance of the center of mass for the rigid body, the composite rigid body that consists of hemisphere and cone, is located at 2.7 R, measured from the vertex itself. So here we'll put down, yes, it's a chop, proven. All right. Now I hope that is clear for this section here. Now next I'm going to present to you another way to actually evaluate the center of mass if we change the our frame of reference, right? Stay tuned. Right. This is the second approach that different students might take. Okay, if you don't actually put your frame of reference at the vertex itself, but instead you put it somewhere like the one that is shown here. Okay, so how can we obtain the same answer even if your reference frame was not positioned properly, okay, according to what the questions want. All right. Let's give it a go. Now I have keep some of the calculations intact because they don't actually change much, even though your frame of reference is very different from previously. Right. Now you can see that the volume of the cone will still remain the same. The mass will still remain the same. The hemisphere will still remain the same volume, the same mass. The composite would also be the same. Okay, now the only thing that is difference now would be the um, the center of mass for the cone with respect to the frame of reference that you have already set up. Okay, now just let me label this one more time. So this part is the vertex here. Okay. Now we know that the center of mass of the cone when measured from the vertex is 3 over 4 here. But because our reference frame is here, so therefore we are interested to find out how far is the center of mass for this cone here, label it GC, with respect to the frame of reference that we are using. That one must be um, 1/4, 1/4 of this, because this whole thing is 3/4. Okay, this part is 3/4 of 3R, and then this one must be 1/4 of 3R. Right, so I hope that is clear. Now if you set up your frame in such a way, the measurement for the center of mass for the hemisphere will be easier. Okay, now before that, just let me rewrite this. Yeah, one more reminder, if you put your frame of reference in such a way, because your center of mass is below, based on Cartesian coordinates, this is a negative coordinates. So here is better I put in a negative 3 over 4r. That is the only thing you need to pay attention to if you set your reference frame in such a way. Okay, and then the center of mass for the hemisphere with respect to the center, which is 3 over 8. We have referred to the data booklet previously. Okay, so this is 3 over 8 here. Okay, so that is very direct. I just need to put that in. Right, now you'll notice that if you are using this method here, there is less risky. There will be less steps that we might have forgotten to take. But the only catch is negative. That's the also a very risky steps that we need to pay attention to. Right, now from here itself, we're going to apply the same strategy. The sum of each individual moment must be the same as its moment for the composite body. So I'll still label this as this. Okay, now from here itself, the same strategy apply. So there will be 5 over 3 rho a y bar here, and then it will be the sum of all this. And, the first one will be negative 3 over 4, and then the second one will be like, in this case it's quite obvious, is a quarter. Did I get it right? Is it quarter? It's not quarter. I think I mistakenly I omitted the R just now, so please forgive me with that. I think this is supposed to be a 4. Yep, this is a 4. Just let me correct that. So from here onwards, I would have, in this case, it's negative 1 over 2 rho pi r 4. Okay, that should be correct. Okay, now from here onwards, my center of mass with respect to the frame of reference that I'm using, that will be negative 3 over 10. Okay, 3 over 10r. So negative 3 over 10r. Okay, so negative 3 over 10r. So negative 3 over 10r means is somewhere below here. Somewhere below here. So negative 3 over 10r. Okay, now I have indirectly obtained my center of mass with respect to the frame of reference that I'm using. Okay, now the last part will be I need to find out the uh, center of mass of this composite body with respect to the vertex itself. With respect to the vertex, like how far would this be, for instance? Okay, this is the one that they want. I just put in a star here. So therefore, this part here would be, of course, it's very obvious, is just 3r subtract off with y bar here. And then there will be 3r. Okay, now when I say subtracted, I wouldn't take into account this here. I'll just take into account the magnitude itself. So that will be 10r, and then that will give me 27 over r. And then there you have it. I managed to prove this using a different frame of reference, right? I hope that is clear for your learning at this point, right? Okay, stay tuned. I'm going to move on to the next question shortly. All right, this is our second question. A light inelastic, oh sorry, it's a light elastic string has a natural length of A, modulus elasticity of 24 mg. Now, one end of the string is attached to a fixed point A there, according to the diagram there. The other end is attached to a particle which has a mass of 2m. Now, we need to find in terms of A, the extension of the string when the particle hangs freely in equilibrium. All right, now in this question, this is very clear because it mentioned that it is in equilibrium, which means velocity is equal to 0, acceleration is equal to 0 also. Okay, and then now there are like, you might have a thoughts of two strategies that you can use. The first one is by using Newton's second law, and then the second one you might be tempted to use conservation of energy. All right, let's see whether it works or not. Is there any conditions that we have to take into account before we can work out this? Right. Now, the first method we're going to use Newton's second law, right? Since it's indicated that it is in equilibrium. Right now, before you start to answer any types of questions that involve mechanics, it's always good to label all the forces that is acting on the system itself. Right? Okay, so when it's hang in equilibrium, I assume that there will be a tension here, and then there is a weight. Oops, sorry. Let me clean that up. Okay. So there's a weight of 2 mg here. Okay. And then it has a natural length of A. I just make assumptions. The natural length of A might be somewhere here. Okay. And then it will have its extension. Right now, up to you how you want to label your extension. Maybe you would like to label as E or X. Doesn't matter. Okay, now that is generally how it actually look like, all the forces that is acting on the system, and then knowing all the parameters involved in this system itself. Then we're going to choose the strategy. Here we say that we wanted to try Newton's second law, so we're going to use Newton's second law. Right now, Newton's second law states that the acceleration is directly proportional to the resultant force. Okay, now therefore mathematically we can write down like this. Where A is the acceleration, the mass is the m is the mass itself. Right. Now resultant force. A resultant force is given by the weight, and then okay, reduce that with or deduct that by the tension itself. So in this case, you have the weight subtract off with the tension that would yield the acceleration. But because the system is in equilibrium, therefore in this case it would be zero, 0 meter per second, right? And then if we try to simplify this, we found that tension is actually equal to 2 mg. And then by using Hooke's law, okay, by using Hooke's law, we know that tension is given by the modulus of elasticity divided by its natural length and then multiplied by its extension. Okay, let me write down all the parameters that involve here. Now the natural length in this case would be label natural length would be an A, and then the modulus of elasticity is given by 24 mg here, right? And then therefore we are good to go at this point. We're going to substitute this as 24 and then divided by the natural length and then extension is right. Now that's how the tension of the string would look like when it extended E. Now by equating these two equations here, we will be able to, okay, now in this case I'm going to label it 1 and 2. We know that 1 and 2 is the same. Okay, now therefore we will write this as all right, and then from here we can conclude easily the extension is 1/12A in this case, right? So I hope that is clear. By using a very simple Newton's second law and Hooke's law, we will be able to deduce its extension when the system is in equilibrium. All right. Now I hope that is clear at this point. Okay, cool. Right. Now I'm going to pause for a while. I'm going to show you a bit of maybe misconception that some of you might encounter while trying to solve this simple question using conservation of energy, for instance. Right? Stay tuned. All right. The next section here, we are still looking at 2A, but I'm going to show you a bit of misconception, or I would say a partial applications of all the informations given here, right? Some student might be tempted to use conservation of energy because it looks quite similar to some of the questions that you have attempted in this case, right? Therefore, you would start to use conservation of energy. Okay, now let's use this conservation of energy blindly without any detailed thoughts in this case. So I'm going to use conservation of energy. So conservation of energy principle here, right? I would say that the energy at A must be the same as energy at B here. So I'm going to label it B. So the total energy at A must be the same as total energy at B. Okay, and then therefore you will start to apply this conservation of energy, saying that at point A there is a zero kinetic energy. Okay, I'm going to put that in, and then there is a zero gravitational potential energy, and then at the same time there is also a zero elastic potential energy because the string is not tension, it's not tau. Okay, so therefore you will say that is 24. I just plug in all the value there. Extension is 0. And then it will be the same as the total energy at position B. Now we know that it is in equilibrium, therefore we know straight away the velocity is 0 meter per second, and then at the same time acceleration is 0 meter per second square here. Therefore, by using conservation of energy at position B, we will be able to get something like this. Oops, I shouldn't be using m because the mass is 2m, so I'm going to put that in square. And then at the same time, um, it actually gain elastic potential energy. So it gain elastic potential energy here. That would be, I'm going to write down here. You would gain elastic potential energy 24 over A. Okay, now the formula for elastic potential energy I just write down at the side here for reference. So elastic potential energy is given by half lambda over the natural length multiplied by the square of the extension. Okay, so this is the square of the extension, which we don't know at this point. And then at the same time, there is also gravitational potential energy. Okay, right. Now that depends on your reference also. So take for instance, if we put this as our reference, then our gravitational potential energy would be 2 mg. The h itself. So the h itself will be a plus e here. All right. It's negative because it's below our reference frame in this case, right? So I hope that is clear at this point. That's how you would like to use your conservation of energy at this point. All right, so if we do a bit of cleanup and so on, we notice that the left hand side are all 0, and then therefore we're going to simplify everything as 24 mg. All right, now that's how it would actually look like in this case. All right, and then from here, if we try to simplify that, I will get 6 over a e square equal to a plus e here. Okay, and then do a bit of algebra manipulation. So I sort of get here um, minus, let me see here, what do we have? Minus ae, and then minus a square equal to 0. Okay, so that's how it will actually look like. Okay, now from here, how can I solve this? Of course, this is a very simple quadratic equations here. Therefore, you can actually solve it quite easily, I would say. All right. So in this case, you can actually solve it as, let me see, 3a plus or minus. Okay, I try to put this one first. Okay, let me check whether I got it correct. All right, I think my sign is upside down. It should be the other way around here. So this one is negative a. So just let me check one more time. It's a 6 is a negative a e. Yep, correct. And then a negative a square. And then from here, I noticed that the 3e plus a must be greater than 0, of course, because extension is greater than 0. A is definitely longer than 0 itself. Therefore, uh, okay, therefore, I can say that my extension is basically just half a a, knowing that 3e plus a is greater than 0 there. Right, it looks like I'm a happy man here. Okay, but hold on then. Okay, what went wrong here? This is the main misconception. So what is wrong with this? Okay, Now I'd like to point out here before we move on to the B, you can see that for the second sections of question 2, we will be applying the same strategy again, right? So the misconception here is, based on the question itself, we have no idea whether the object was released from rest or not. Okay, this one we are not sure. Okay, this one, yes, because we place our reference here. Yep, the gravitational potential energy is actually zero at that reference itself. And then yes, if we start from here, yes, the gravitational potential, sorry, the elastic potential energy is definitely zero. So the only thing we are not sure of is whether the object was released from rest or not. Okay, if if it was released from rest, then our equations would be correct then, and then the extension would be half a A. Nothing wrong with that. It would extend more as compared to the answer that we have already obtained, which is A over 12 there. The correct answer is A over 12. It's not E equal to half a A, because the first conditions was to hold the particle so that it is in equilibrium at position B. You let it be at rest or at equilibrium at position B, not releasing it from position A until it fall and then it reaches equilibrium on itself, right? You can actually release the object from A and then let it fall, and it's going to bounce up and down before it can reach equilibrium. So let's wait like a few minutes for it to reach equilibrium. So once it is in equilibrium, then we are going to apply the Newton's second law there, right? So the correct way to solve this is by using Newton's second law at the conditions of equilibrium here, right? So we shouldn't be using conservation of energy here, because if you use conservation of energy, what is stated here is the extensions would be half a A if it was released from zero, and then when the object has reached instantaneous rest, which we also make an assumption here. Okay, right? Instantaneously at rest, I did mention in my previous videos before, doesn't mean that it's at equilibrium. It just means that at that moment of time, the object is going to change direction. It's going to change direction, acceleration is not zero. So these are the two misconceptions that we have indirectly committed. So this is the one thing I want to clarify for some of you who wanted to know more as to why we can't use these methods here. All right, so I hope that is clear. Let me summarize again. The correct answers to this question is by using Newton's second law. If you want to use conservation of energy, um, yes, by all means we can, but due to lack of information, right, we can't. So these methods fail because of lack of information. All right. Okay. I hope that is clear. Next, I'm going to move on to section B, which we're going to reapply conservation of energy again, but with more inputs of information. Right. Hopefully, it will be helpful. Okay. Stay tuned. All right. Question 2B. The particle is released from rest at A. Now you can see that more informations are given to us. If we have this information, yes, maybe conservation of energy can be utilized in this case. All right, we need to find in terms of A the distance of the particle below A when it first comes to instantaneous rest. We can see that more informations now. We sort of get a full confidence on how to apply conservation of energy now, right? Now, just to show you a simple simulation as to how it would actually look like. Okay, right? You can see that it's going to fall at rest, and then it's going to reach instantaneous rest. I assume that when it reach instantaneous rest, the string would be taut. That is the whole idea there, right? Now let me put in more informations here. Okay, so in this case, let us put in all the information one more time. Now we know that we have the modulus of elasticity, which is given as 24 mg. The natural length is A. Okay, the mass itself is 2m here. All right, and then the formula for elastic potential energy, I just rewrite that again, is 2L multiplied with E squared there. Always remember the E square, yeah, because I also make mistake on the E squared itself. Right? Now the same thing, I'm going to label this before I start. Now when you reach instantaneous rest, I would you have to be very clear. Instantaneous rest means velocity is momentarily zero, momentarily, because it's going to bounce up. It's going to retract in the opposite directions again. But bear in mind, acceleration is not equal to zero. Okay, now we will still have the weight here, so I just label that one more time. We do still have the tension itself. I just put the tension here, but this tension may not be the same as the tensions when the system was in equilibrium, right? And then I would say here, this is the natural length, and then it would be extending. Maybe here I'll label as E1 then, so that we don't confuse this extension and the previous section 2A extension. This is the new extensions when the object was released from position A. It should extend more, of course, right? If you just release it and then make it to equilibrium, then the extensions will be less than when you just release it and then when you reach an instantaneous arrest. Those are the two different conditions there because of the gain in gravitational potential energy. Therefore, it would be extending longer than when it was in equilibrium, right? So I hope that is clear. Okay, let's check through if we have all the informations stated. Yes, we have that. And then now we are good to apply conservation of energy. So I'm going to write that down again. We're going to use conservation of energy principle. Now again, uh, depending on how you want your reference to be in this case, right? So take for instance, this time I'm going to change the way how I use it. I'm going to state that this is my reference now, my frame of reference, which is at this position here. Okay. All right. Using this frame of reference, um, now the total energy at A must be the same as total energy at B. Exactly the same due to conservation of energy. And then at A, kinetic energy is zero, so I don't have to include that. And then with respect to my frame of reference there, the um, the object or the system would have gravitational potential energy in this case, which is 2mg. The height would be A plus E1 here. Now that would be the gravitational potential energy. And then gravitational potential energy is 2mg, A plus E1. Elastic potential energy. Okay, elastic potential energy at A is zero. So I can omit that. Kinetic energy is zero. I can omit that. All right, therefore, that's the only energy that I have at position A by using this reference frame, REF equals zero. And then at position B, this is position B here. Okay, at position B, now there is no kinetic energy either because it is at instantaneous rest. Now, other than that, it would have gained elastic potential energy. Okay, it would have gained elastic potential energy. And then elastic potential energy is given by this formula here. Just plug in all the value here. mg over 2a multiplied by its extension, so extension square. And then there you have it. There's no other energy component that we need to take into account at this point of time. All right, and then there you have it. We're going to solve this as usual also. So in this case, we will have like what do we have here? We have a squared plus ae1 equal to 6e1 square. And then by rearranging this again, like what we did before this, okay, since we have done this before, so we know this precisely. It would look something like this. I hope I got it right. Okay, just let me recheck again. Yep, that's how we factorize it. And then from here, we can conclude that the extension, the new extensions will be half the natural length because the 3e1 plus a must be greater than 0 in this case. Right. So now we know that when it reached instantaneous rest, it would have extended half the natural length. Therefore, to answer the question itself, the distance of the particle A when it first come to instantaneous rest. So distance of particle A below A, particle below A here. So the distance with respect to this position here, it will be A plus A over 2, which is 1.5A then. And then there you have it, right? By using these informations that we have collected. All right, so I hope that is clear. Now, next, I'm going to present to you another way to actually solve this. Just changing a bit of the algebra itself. Okay, but I personally I prefer this method compared to the method that I'm going to present to you next. You will see the reason in a while, right? So let me erase all this because it looks more or less the same. The only difference is just the representation of the informations that we have. Okay, now I'm going to maintain my reference frame to be here. Instead of calling A an extension here, I'm just going to answer directly what the question wants, the distance below A. So I'm going to call this X then, XA, the distance below A, which is actually A plus E1 here. Yeah. But in order to fulfill the question directly, we can look for XA directly. And then we don't really need to perform any addition in this case, right? But the way we apply the conservation of energy is still the same. What we have here will be gravitational potential energy. So I'm going to write that down again. 2mg, instead of writing A plus E1, I'm going to replace that with XA. Okay, and then elastic potential energy, which is 24 divided by A. Oops, I think I need to divide by 2 also here. It's a good reminder, always write your formula here. And then multiply by its extension. So this extension, you can see that extension is basically XA. There's a pro and con here. If you are a positive person, you may not be want to use this method because there's a negative here. That's just my personal thoughts. Right? So E1 square, therefore it means XA minus A square here. Right? And then if you sort of simplify all this, we will end up with 6. I'm going to put my A over to the other side. You would actually end up here. And then of course with a bit of algebra manipulations here, All right, so it will look something like this. Let me rearrange that neatly so that we can see what we can do from here. All right, so from here we can see that we will be able to factorize this um, quite easily. So that would be something like this. Oops, I think I did done it wrongly. Hold on. That will be 2xa now because it's 6. Right. So from here we found that we can have 2 over 3a, or xa could be 1.5a. Which was the correct answer. We already knew that from our first approach there. But uh, the thing that you want to figure out is why can't I accept the second one there, right? Now, therefore, we say that XA is equal to 1.5A because this 2 over 3 is less than A. Oops, what am I saying? Yep, because this 2 over 3a, which is the total length measured from a itself, is less than its natural length, which means it's impossible, knowing that the string was tau. Here I need to make another statement. The string is tau. Yeah. The only way that the object can reach instantaneous rest is when the string is tau. So that's the reason why we accept the distance measured from A as 1.5. From here, we can get the answer directly without addition and subtraction, but we indirectly incorporate that into our algebra, right? So that's one of the reasons why I still prefer my first method compared to this one here, because you need to sort of reason with one of your solutions there, right? So I hope that is clear for the second question here, right? We're going to move on to the third questions shortly, so stay tuned. All right, third question. A particle P or mass mkg falls from rest under gravity. There is a resistive force of magnitude mkv square Newton, where v is the speed of the P after it has fallen a distance x, and k is a positive constant there. Right? Now, by solving appropriate differential equation, we need to prove that the velocity square is given by this exponential equation. Right? Now, before that, let's take a look at how the motion look like, and then we are going to incorporate all those parameters before we try to solve this. All right, now you can see fall under the influence of gravity. Okay, now that's how it look like. I put in a reference line here just to show that this is where the whole um, frame of reference is located. So here I just write it down as my reference frame in case I need to use conservation of energy, for instance, right? Okay, now as any types of mechanics question, we are going to incorporate or label all the forces that is acting on the object. So in this case, we have the weight, which is given by, let me see, mg here. Okay, and then at the same time, there is a resistive force acting on the particle. This is m kv square here, right? And then we assume that there's no other forces that is acting on the object at this point. Okay, other than that, the distance x fallen. So the distance x is measured from our reference point here. That's the reason why we need to use a reference here. I'm saying that the x was referenced from here. Okay, now the x is increasing in the directions downward. So the displacement was with respect to that reference frame that we have already set up. Okay, and then the speed is also in the same direction. It's moving downward in this case. Initial speed was 0. Okay, now that's how it looked like. Right? So for this is better, if you look at the equations that we're going to prove, is better we use Newton's second law here. Right? So we're going to use Newton's second law. Acceleration is directly proportional to its resultant force. Okay, so ma in this case. Of course, originally it was ma. You can also write in its differential form, second derivative, for instance, with respect to time. Okay, but based on the equations that we're going to prove, there is no time parameter involved. So therefore, you might want to obtain another differential form, which is given by v dv dx here. Okay, now that is also another version of Newton's second law, right? So from here, the resultant force is given by, because it's falling downward. Now, therefore, I'm going to write down that as mg. Okay, and then there you have it. And then by performing a bit of simplification, we will end up here. Okay, and then there you have it. Now we need to solve this first order ordinary differential equation here. Yep, we notice that the variable are separable, meaning that you can actually separate the variable itself. Therefore, if you separate it, it will look something like this. Okay, now that's how it look like. And then to solve this, we have to perform the antiderivative both sides here. Right. Okay, now for this question here, just to recap on your integrations, we can actually solve these integrations by using substitution. So I'm going to write down its substitutions at the side here so you can see what's going on. From here, we will let u equal to, okay, since u is initial velocity, I won't be using u. Maybe we'll call that y then. So let y equal to g minus kv square. Right, now we can actually differentiate this with respect to v. That would give us 2kv from here. And then you will notice that your dv, in this case, because we have dv, so dv is actually equal to, I can say that v dv, because there's a v dv there, is equal to 1 over negative 1 over 2k dy there. Okay, now from here onwards, we can substitute this into here. We notice that v dv is actually this, so the whole thing can be written as this. And then this is actually y, therefore it will look something like this. And then the integrations here would still remain the same. Okay, and then there you have it. So I hope that is clear at this point. Okay, now from here, integrating this with respect to y will be quite direct. It's just 2k ln y. This one become ln y itself. But y, because we are using this substitution, so therefore we have to substitute this one back because y is given by this. Therefore, it will be kv square. It's always good to put a modulus sign here because I have no idea whether it's going to be positive or negative depending on the setting itself, x plus a c here. Okay. Now from here onwards, we are going to figure out what would be the constant. All right. Now there are a few informations that we need to make use of. Okay. Now first of all, at x equal to 0, you can see that at x equal to 0 here, initial velocity was 0. So therefore, we're going to substitute that into here. When x is equal to 0, the v itself, is equal to 0. So we're going to substitute that. Initially, it was released from rest. So therefore, it's 0. Okay, by solving that, you will find that the c is basically negative 1 over 2k. This one is 0, just ln g. Since I know that g is positive, I can leave out I can ignore the modulus sign. Okay, now from here onwards, I can rewrite this equation as, okay, so I can rewrite as this. All right, and then there you have it. All right, now that's the equations that we have at this point of time. Okay. All right, now I'm going to pause for a while. Make sure you know what is going on with your integration, setting up the first order ordinary differential equation through the applications of Newton's second law here. All right. Okay. Now next, I'm going to um, polish up this equation so that I can satisfy what the questions want. All right. Now let me clean up the rest. We don't need this anymore. We only need that final form that we have here. Okay. I'm going to rewrite this. This one looks something like this. 2k All right, that's how it look like. And then we can combine these two terms together. Therefore, we will get something like this. For simplification, I just ignore the modulus sign. Okay, that's how it look like. And then we can simplify this as okay, that will be 2kx. And then will be exponential. Then therefore we can finalize that as g over k 1 minus exponential 2kx. And then we manage to, okay, hold on this. Then we managed to prove this, proven. Okay. All right. So I hope that is clear at this point. Do check through if you are okay with this. All right. Now we managed to prove that differential equations, the solutions to the first order ordinary differential equation, right? Okay. And then there you have it. That's 2a. Now stay tuned. I'm going to move to 2b shortly. All right. This is the next section of question 3 now. It is now given that k is equal to 0.01. The speed of p when x becomes large approaches v. Now we need to find the v correct to 2 decimal places and then hence find how far p has fallen when its speed is half a v. All right. Okay. Now first of all, we're going to substitute this k value first into our equations that we have already solved. Therefore, in this case, we will get v squared that will be 100 G here. Okay, this one will be negative 0.02 x. Okay, now that's how it look like. As x become large, so in this case we want to find v here. So as x approaching infinity, so like extend through a very long distance here, the v square would be as x approaches infinity. All right. Now we know that as x approaching infinity, when it become very large, the exponentials component would eventually diminish to zero. Therefore, this whole v square would be equal to, in this case, would be 100 g. Yeah, would be 100 g. Or in this case, we say that the v would be approaching. Okay, hold on. In this case, you can sort of square root this. So therefore, v will be equal to, what do we have here? We have like a 10 root 10, 10 root 10 there, right? So if you take out your calculator and try to calculate this, right? So using the result from the calculator, you should get yourself 31.662 meter per second. All right, and then there you have it. As the x approaching infinity, the velocity will be approaching 31.62 meter per second. Right? Now I hope that's clear. Now next we're going to look at the second section. Hence, find how far p has fallen when its speed is half a v. Okay. Oh yeah. In this case, I better write down this v would be here, 31.62. So for number 2, how far it has fallen when the speed is half of this. Okay. All right, now let me erase off this. We have a v square over here, so I'm going to use that again. Okay, so I'm going to use that. From here, when it's fallen half a v, so when this is fallen half a v, and then that would be typically half a v we have it here. So maybe for a complete answer, we will write it down as 10 sub 10 here if you want. Basically, this is just 100 G to be precise. Okay, that will be square the whole thing. Yeah, just to be sure, this is a square of the whole half of V. Okay. Okay, and then there you have it. Okay, from here, right? And then we know that this is actually 100 G. This is actually 100 G, so we can actually cancel out 100 G with that. Therefore, we have a quarter here. This is another 100 G. X there. All right, so that is typically, if we use G as 10 Newton per kg for simplification, now that will be 25, 250. Okay, and then from here itself, we will have a problem. Hold on, let me see if I got it. All right, this is half a v. There will be half a v here. Cancel off with this. 1 minus, did I get it right? There's 1 minus. G over K, 100K. This is half a V there. Half a V. Oh, yep. I think did I mistakenly copy down? Oh yeah, I did identify my own mistake here. Okay, let me correct that. Yeah, I think that is a V. Yes, correct. That is actually a V. This is actually a V square. So if we actually apply this, right, this is actually a quarter. All right, I think that is my main mistake. So sometime in the exam, you might accidentally make some numerical error here, but never mind, as long as you understand where the error is. I think this one is just a quarter. Yep, that's my. I shouldn't have made that mistake, but anyway, it's cool. Okay, now from here, I will have 0.02x, which is equal to 3 over 4. Okay, and then from here onwards, your x will be, you will get a ln 0.75 divided by negative 0.02, and then that will be how far it has fallen in this case, right? So let me get my GeoGebra here so that we can tabulate this. Okay, hold on. So 75 divided by 0.02 there. So therefore, the distance that the object has fallen is 14.38 then, if you want to leave it as two significant figures. Sorry, two decimal places. 14.38. And that will be 38 meters. Just let me check in case I miss out. Is it 38 or 28? Yeah, correct. Right. So therefore, the particle has fallen 14.38 meters when its speed is half a v. Right. So I hope that this one is clear to you. Just let me make some remark here so that we know what we are writing here. So when the speed, okay, when the speed is half a v, which is actually half of 10 square root of 10 here, which is actually 5 if you want. All right, and then there you have it. Right, by solving this, you'll be able to reach the conclusion. All right, now stay tuned. I'm going to move on to the next question shortly. Right, our next question is on oblique collision. Now you can see that there are two uniform smooth spheres A and B of equal radius, have a mass of m and 2m respectively, according to the diagram there. Sphere B is at rest on a smooth horizontal surface. Sphere A is moving on the surface with speed v at an angle 30 degree to the line of center of A and B when it collides with B. Now the coefficient of restitutions between the sphere is E here. All right. Okay. Take your time to read through one time here. Okay. Now for any types of oblique collisions in this setting, it's always good to label the horizontal and vertical component of its velocity. Velocity in this case, right? Okay. Let's look at the question first before we start to label that. Okay, hold on. Let me get this. All right, now the first question. Show that the speed of B after the collision is given by cert3 over 6u 1 plus e, and find the speed of A after the collisions here. All right, so in this case, I have already draw another diagram to represent the collision after the condition after the collision. All right, so this diagram here represents before the collision, and then this part represent after the collision. Right, now, as I mentioned before, it's always best to label the initial velocity and all its component. Now you can see that its vertical component of the velocity, I'll label that as ux. That is given by, it's the same component here. If you make this as your right angled triangle, if you resolve it using your trigonometry, you will find that your ux, which is, sorry, ux, I keep on writing x there. Let's call this vertical component, uy. So uy will be given by, because it's upward, so that is u sine 30. U sine 30, sine 30 is actually a half, so therefore that will be u half here. All right, so I hope that is clear. And then next, the horizontal component, which is given by here, and that one I will label as ux here. Okay, so ux will be given by u cos 30. And then we know that cos is sec 3 over 2 u here. All right. So that's the first step. Right? And then also we need to label what will happen after. Okay, as usual, I'm going to label this as A, this is B, and then it has a mass of m2m as a reminder. Okay, so what would be the velocity component for A after collision? And now this is a rule of thumbs when it involves oblique collision. The vertical component would not change, because the main impulse involved in this oblique collision is the horizontal impulse. And then assuming that the surface of the sphere is smooth, therefore there is no vertical impulse here. Right. Now, knowing that facts and assumption, so therefore we can label the velocity of the uh, component or the particle A after collision. After collisions, it will be the same. So that will be here. After collision, I'll label that as Vy will be the same. Right? But the would be the same as, yeah, I almost forgot that, would be the same as Uy here. Right? But the horizontal component of the velocity after the collision, that would change. So this one we will label as Vx. This one we are going to figure out later. And then as for B, exactly the same. The initial component for B, the U, Uy, Uby here is 0. And then Ubx is 0 also, initially. Right? Okay. Therefore, after the collisions, as I mentioned before, the vertical component never changed. Therefore, the vertical component of the velocity of v after the collisions would remain the same. So here I will use w instead. So it will remain as 0 meter per second. But yes, the horizontal component of v will change. This is the one that we need to figure out shortly. Right? So I hope all these informations are clear. First step is to label all the component of the velocity before we start to apply. There are two principles we're going to apply for these oblique collisions. The first one will be conservation of momentum, making assumptions that there is no external force acting on the system itself. All right. Okay, so from here we're going to use conservations of momentum. Okay, first step, conservation of momentum. Right, by using conservation of momentum here, we know that the total momentum before and after must be the same. So total momentum before, now because we have two components of velocity, therefore we're going to focus our conservation of momentum only for um, horizontal component. So here we will consider by considering consider uh, x component, which is the horizontal component. Right. Okay, so I hope that is clear. We're only interested in the horizontal component because this is where the impulse involved or the impact involved, right? So total momentum before collisions is given by mux plus 2m ubx must be the same as m Vx here plus 2m wx. Total momentum before after must be the same. And then if we try to simplify this, ux, we have found that out, which is this. ub was 0. And then vx, we have no idea. And then wx also, we have no idea. And then by rearranging this correctly, okay, now that will be my first equation. Right? Secondly, I'm going to use Newton restitution law. So Newton So using Newton restitution law, the same thing, my focus would be on the x component also. Right? Relative velocity of separations over relative velocity of approach must be the same as its coefficients of restitution, which is e in this case. Right? Now that would be relative velocity of separation over relative velocity of approach must be the same as E. I know that most of the textbook are using this version, negative E, right? But I'm not a negative person here, so I prefer to use the positive version. If you prefer the negative version of it, you can always use it, but they yield the same result here, right? Okay. So from here itself, we will be able to form the second simultaneous equations. You can see that I just rewrite it neatly. You can see that this is actually set 3 over 2 EU. Now that will be my second equation. And then solving this should not be a problem. Okay, I can take like 1 with 2. So if I take 1 with 2, I will get 3. Yeah, that would be okay. And then of course from here 6. Okay, now bear in mind that is not our answer. That is just the horizontal component of velocity of B after collision. After collision. Okay, but the speed is I'm going to show it to you. The speed. Okay, the first part, speed of B after the collision. Okay, so speed of B after the collision is actually given by is a square root. Okay, so bear in mind. And then from here itself, we notice that the vertical component of the velocity after collisions for B is 0. That's the main reason why the final answer is actually equal to this one, meter per second. All right, so I hope that is clear. We have successfully proven the first part. The speed of B after collision is given by this equation here, right? Now next we're going to make use of all the result that we have to find out the speed of A after the collisions. But at this point of time, after solving for Wx, we can also find Vx here. So I'm going to work out the Vx. Okay, maybe I'm going to work out the Vx shortly on top here. Just let me clean this up. Just let me clean this up properly. Oops, I think I indirectly clear the other one. Okay, but it's okay. I'm going to rewrite that again. The two of the simultaneous equations will be here. The first one was here. That's my first. And then second one is here. That's my second one, right? So I have already found my Wx, which is this. Okay, now I just need to solve for my u. Sorry, not u, Vx. Okay, just let me clear everything. Okay, so for Vx is quite obvious in this case, so maybe I'm going to use that. That will be surd 3 over 2u minus of surd 3 over 3, 1 plus e u here. Okay, that is typically, I can actually write down like this. 6 for instance, I just place my u outside, it's easier. So 6, this one will be a 3, and then this one will be a 2, 1 plus e. Okay, and then that would yield, what do we have here? Surd 3, 6, and then that will be a 1 minus 2e. And then there you have it, right? And then finally, the speed of A after collision. So speed of A, as usual. So speed for A is v square plus y square. Okay, and then Vx is over here, and then my Vy is the same as Uy because there's no impulse in the vertical component. Then therefore that will be half a u here. So therefore I'm going to put this one in. Square plus half a u square. Square root that. All right. And then by simplifying, okay, just let me try to simplify that. That will be a 6, 1 over 6 there, 9, and then I can take out a root 3. So therefore it'll be root 3, 6. Okay, root 3, 6, and then this one will be 1 minus 2e square plus, oh yep, I think I missed out one section here. I forgot my u. Yeah, there's a u here. Okay, I better put it in. And then from here, after I simplify that, I should have a u here. And then that should be a 1 squared. Okay, so from here onwards, let me see what do I have. I will have cert 3 over 6u. And then this one, if you try to simplify that, you would get, let me see, it's a 4, it's a 4, 1, 2. Is that a 2? That's a 3. Oh, yep. I think I missed this one out here. I have a 3, this part, sorry. Just let me correct that. This one will be a 3. Okay, so from here itself, you will end up with 4e squared minus a 4e plus a 4 square root. Okay, and then further simplifications, eventually you will end up with, okay, hold on, this one is 4, you can take it out, that will be, okay, I try to simplify that much more. Eventually you will end up with this. I think it's e squared minus e plus a 1. And then there you have it. That will be the speed of A after collision. All right. So I hope that is clear. Do check it out. If you do make mistake, you can always come back, especially the U part. I might accidentally forgot to write it down. So do pay attention to that. A lot of the square roots expressions they need to be very careful of. All right. And then there you have it. This is section A. It takes a long while. All right, stay tuned. I'm going to show you the second section shortly. All right, now given that the restitution's coefficient is 1/3, we need to find the loss of kinetic energy as a result of the collision itself. Right? Okay, now this is before, just as a reference one more time. This is after. Okay. Okay. Now, in this case, we have already found out the speed for A after collision. It was u over cert 3. U over cert 3, yep. This one will be e squared minus e plus 1 square root. And then we have also found out the speed of B after collision, which is over 6, 1 plus e u. Okay, these are all the informations that we have already obtained. All right. Now the loss of kinetic energy. Okay, before that we're going to substitute the E inside. Having the E equal to 1/3, or VA would be, okay, so 1/3 here, there will be 1/9, 1/3 plus 1. Okay, so from here, let me see what do we have here. That would be a, let me see, it's easier to do it this way. It's 2/3 to the 677 over 9. Is it 7 square root of 7, 9? Did I get it right? Just let me check properly. 6, 7, 6, 7, 9. Yep. Okay. So that is cert 7 over 9. Cert 7 over 9. And then that would be, so it would be u cert 7 over 3 cert 3. Okay. Or you can actually write it down as 7 over 3, 1 over 3 u then. Okay. And then for the speed of B, we will have 1 plus 1 over 3 u. Okay, so from here there is a 4 over 3. Okay, 4 over 3, I just write that down. Three, 4 over 3, is it? Is that a 3? Yeah, correct. So there's a 9 u. Okay, and then there you have it. That's the speed. Now we are interested to find out the loss of kinetic energy. Now, usually we would prefer to find the change in kinetic energy. So the change in kinetic energy usually is the total final kinetic energy subtract off with the total initial kinetic energy. So total, I'm going to do B first. So B is this one here. We square the speed of A is this one here. Yeah, maybe I'll just write it down as this one will be 9, 3, 27. Okay, I just square directly. And then this is this is final kinetic energy. Subtract off with its initial. So for B, there is no kinetic energy here. But for A, yes. Okay, for A, it's just U. So U square. Okay, just let me try to finish this. This one will be M. You get a 4, 27 here, U square. Plus 7, 54 mu square, subtract off with half mu square. Okay, so from here we have let me see here, 8, 15, 54, 2, 8, 8, 15, 54 mu square, subtract off with half mu square. And then here you will take 27 here. We will have 12, negative 12 over 54 mu square, or you can further simplify that as negative 4 over oops, let me see, 4, is it 4? Did I get it right? Okay, hold on. I think 3, sorry. So 8. So that is actually 2 over 9. So negative 2 over 9. Mu square. All right. Now there is a change in kinetic energy. Therefore, if you want to finalize the loss of kinetic energy, because it's negative, therefore it is a loss in kinetic energy. It's 9 over 2 mu square. Joule, if you want the unit. All right. So I hope that is clear. Stay tuned. I'm going to move on to question 5 shortly. All right, question 5. This is a horizontal circular motions question. You have a particle P of mass M is attached to the one end of the light inextensible string of length A. The other end of the string is attached to a fixed point O. You can see that from the diagram itself that the particle P moves in a horizontal circle with a constant angular speed W, with the string inclined at 60 degree to the downward vertical through O. Now we need to show that the angular velocity square is given as 2g over a there. All right. Now before we start, just let me roughly show you how the circular motion actually look like. This is not the best simulations that you can get, all right, but it kind of give you an idea. Okay, now you can see it actually circulate in a circle from P back to P again, and so on and so forth. Right? Okay, now we are ready to solve this. Okay, now circular motions, there are also two principles that we usually use, is the Newton's second law, and sometimes we may need a conservation of energy, but usually conservation of energy is used for vertical circular motion, right? For horizontal, usually we only need the Newton's second law. As usual, you must label all the forces acting on the system first before you start solving this. So first of all, we have the weight acting downward, which is mg, and then we have a tension here. Okay, all right. Now generally those are the only forces that is acting on the system. And then next we're going to apply the Newton's second law. The resultant force is given by ma. Okay, right. Now in this case, the resultant force that contribute to the centripetal force is actually given by T sine 60, and then that would actually produce an acceleration here. And then accelerations in terms of circular motions, there are two formulas that we can use here. You can either use mv square over over the radius of the circle, in this case, over r, or we can actually write it down as r omega square. Oops, something wrong with my omega there. Hold on, omega square. Yeah. But because we are trying to prove the angular velocity, therefore we're going to use the second version here. The r itself is the radius of the circle. Radius of the circle can be obtained by using a bit of trigonometry that is given by a sine 60 degree. If you obtain its exact measurement, that will be sec 3 over 2a. Okay, and then from here we're going to substitute all those, sec 3 over 2a omega square. Okay, something wrong with my omega square. Just let me clean it up. Okay, that's your omega square. Okay, all right. And then now we can sort of simplify this a bit. Okay, because sine 60 is also sec 3 over 2. Therefore, this is sec 3 over 2 is equal to sec 3 over 2 ma omega square. So from here, we found that the tension itself is basically given by ma omega square. All right, now that's our first equation. All right, by resolving it in the directions of the centripetal force. We can also resolve the forces vertically, this direction. Okay, by consider the vertical component of the force, we will have, so by consider the vertical component of the force, this part is the horizontal component. Therefore, we can have T, this angle must be the same as 60 also. So T cos 60 would produce the same force as its weight. That's how you can maintain horizontal circular motions here. Right? Now we know that cos 60 is a half. Therefore, in this case, we have 2 mg here. Now that will be our second equation. Now by solving both of these, you would recognize it directly. That will be ma omega square is equal to 2 mg. And then from here, omega square will be given by 2g over a. And then we have successfully proven this equation here. All right, so I hope that is clear at this point. All right, stay tuned. I'm going to move on to the second part of this question shortly. All right, the next sections of question 5 Now we are looking at the vertical circular motions. The particle now hangs at rest at a distance a below O. So you can see that it's below O. This is A below O. It has been projected horizontally, so we have no idea what is its velocity of projection, but we can label it as U. And then it's going to perform a vertical circular motion in this case. It is stated that when the string makes an angle 60 degrees with the downward vertical through O, the angular speed of v is 2g over a. Therefore, at this point, okay, so it has a angular speed of that value there, all right? And then the string first goes slack when OP makes an angle theta with the upward vertical, meaning that this object, this particle is going to move here. It will have an angular speed of here. So we're going to write that down. Angular speed square then. Okay. We move up here. And then when we move up to this position here, when we make an angle theta to its upward vertical, the strings start to slack. So when they say the strings start to slack, basically it means tension is equal to 0 Newton. All right. Now, before you start, I'm going to show you simple animations again. Okay. So you can see that it's going up there. It make an angle 60 degree, 60 degree, and then after that, it will have a angular speed of square root of 2g over a, and then it continue to move up until the string is slack when its tension is equal to 0. Now we need to determine the value for the cosine theta. Okay, all right. Now let me erase the text. Let's remember what we are supposed to do. We are supposed to find the cosine theta here. Okay, all right. Now let's try this out. So in 60 degree here, its angular speed is given by this value here, right? Okay, so at this point, now we are going to observe its position at P first. So when the object is somewhere here, when it's at position P, for instance, okay, we're going to consider motion at position P. All right. Now, as I mentioned before, when you handle vertical circular motion, it's best to use conservations of energy. So here we're going to use conservation of energy. All right. Using conservation of energy, um, we can compare. In this case, we can compare the total energy at position P and position Q here, for instance. Right? So we state that the total energy at position P and position Q must be the same. Right? Now, of course, whenever we use conservation of energy, it's always best to put in or lay out your frame of reference. Now, in this case, for simplification, I will lay out my reference frame here. So this one will be my reference. And then this object will go up to here. And then we know that the distance between here is actually given by, okay, I'm going to write it down here. So that will be A cos theta is this part here. And then this small section here is A cosine 60. Now you know that A cosine 60 is half. So here I just put it down easily. It's just half of A. Okay. And then there you have it, right? So I hope that's clear. All right, from here, now beside that, if we know the angular speed here, okay, we are going to use that conservation of energy. Total energy at P must be the same as total energy at Q. Okay, now at P we have kinetic energy, which is actually given by half m u. You can say that mvp square, the speed at P itself. And then this one must be the same as the kinetic energy at Q, which is half m vq square. And then at the same time, you also gain gravitational potential energy, which is mg. Now the h itself is given by a cosine theta plus half a. Okay. Now at this point of time, we need to determine the VP itself, the VP itself, or the VP square. Okay. Now we know that VP is actually given by a omega at P here. Therefore, we know that BP square is equal to a square omega P square. Now there goes the same for VQ. VQ is a omega Q here, which means it's the same as if you want VQ square, that would be a square omega Q square. Okay, so I hope that is clear. From here, we're going to substitute this into this equation. We will have half the mass. Okay, now in this case, all the mass can be reduced, further reduced. So therefore, in this case, we have a square omega p. This is omega p here. Omega p square is the same as half. Here I just label it VQ first. And then we have that half AG. If I factorize that, I will have 1 plus 2 cosine theta. Okay, that's how it would actually look like. So if you try to simplify that, we will get VQ square. VQ square is actually equal to a square omega P square. Subtract off with AG. Alright, now that is our first equation. Okay. Alright, so I hope that is clear. And then from here, we can also apply at position Q, we're going to apply Newton's second law. So at position Q, we're going to apply Newton's second law. Okay, so at this point, as I mentioned before, whenever you apply Newton's second law, you must label all the forces that is acting on the object. So we have mg. At the same time, we have tension. So from here, we know that tension plus mg cosine theta must be the same as its centripetal force, which is mq square over a here. But we know that at angle theta, the string start to slack, meaning that t is equal to 0. T is equal to 0 when the angle is equal to theta at this point. Okay, so therefore we can simplify this. VQ square will be equal to AG cosine theta. Right. And then finally, we just need to equate these two equations here. We're going to substitute 2 into 1. We will have A. Now in this case, A omega P. Omega P square is actually equal to this. Now for simplification, I'm going to simplify this as 2ag. There's actually 2ag. The whole thing become 2ag. Okay, and then there you have it. From here, we can remove all the ag there, and then we sort of have minus 2 cos theta equal to cos theta, and then that would help us to conclude that the value of cosine theta must be equal to 1/3. All right, so I hope that is clear for this question 5 here. Stay tuned, I'm going to show you the last questions for this specimen paper. All right, this is our last questions for this specimen paper, question 6 here. It's a projectile motion. A particle P is projected with a speed u at an angle alpha. Okay, I have labeled that wrongly. It's supposed to be alpha there. So just let me label this as alpha here. I change it. Okay. Um, and move freely under gravity. So here we assume that there is no air resistance. The horizontal and vertical displacement of P from or at a subsequent time t are denoted as x and y respectively. We need to derive the trajectory equations for p with respect to x and y there. All right, now before that, just let me roughly show you how it actually look like in this case. Okay, so this is the projectile motions there. Generally, when the object is somewhere in the mid-air, for instance, it has a horizontal displacement with respect to O here, which we label as X. Okay, and then its vertical displacement is labeled as Y here. All right, so this is how it look like. I hope that is clear at this point. Okay, all right. Now, for any projectile motions questions, the most important thing is to resolve its velocity component, the initial velocity component, horizontally and vertically. So its horizontal component is given as, because it's projected at u, so this component will be ux, this part will be uy there. By resolving the velocity, we found that ux is actually given by u cos alpha, whereby uy here will be given by u sine alpha. Okay, I hope that's clear. And then by considering the horizontal motion, so by considering the horizontal motion, we found we can actually use this Suvet or this kinematic equation u t plus half a t square here. All right. Now, if you are interested in the horizontal component, here we will label it as ux. And then for horizontal component, because there's no air resistance, then its horizontal acceleration must be equal to 0. Therefore, this will be can be simplified into x, because we label the horizontal displacement at x is given as uxt, and then we know the uxt is given by this, which is the same as u cosine alpha t. And then from here we can make our t as a subject. That will be x over u. Okay, maybe I'll change it a bit. We can label it x over u secant square alpha. All right, now we have done with the first equation here. Now the second part, by considering the vertical motion, using the same equation again, we will have sy gt square, where its vertical component of the acceleration is equal to negative g meter per second square. All right. So from here, we will have y equal to uy is u sine, and then we know our t. Our t is x over u. Sorry, it's not secant square. I think I made a mistake there. Please forgive me. It's a secant. Okay, so this one will be secant alpha. And then from here, you get x square over u square secant square. Okay. And then by simplifying this, we will get x. Okay. Now sine alpha over secant alpha is actually sine over cos. Sine over cos is actually, yeah, maybe I write it down clearly so that you know what is going on. So this is actually sine alpha over cos alpha minus half g x square over u square. Now secant square, of course, you can change it to tangent square and so on and so forth. But since the questions only want it to be secant square, then we just keep it secant square. And then simplifying this further, we eventually reach this conclusion here. And then there you go. That is the proof for the trajectory equation, right? So stay tuned. I'm going to show you the next section B there. All right, now these are last sections here. B, the greatest height of P above the plane is denoted as H. When P is at the height 3/4 H, it has traveled a horizontal distance D. Now this is merely the substitutions of all these values into its trajectory equations here. Now what that means is when it's at height, so it means when the y is at 3/4 h, its x value is equal to a d here. Now knowing that tangent alpha is equal to 2, we're going to substitute all this value into here. Then we're going to find all the possible values for d. Okay, so from here we have, let us substitute in. We have d, tangent is a 2, g, x is a d square in term of h. Okay, in term of h. Okay, secant square. Secant square is 1 plus tangent square. So we can use that identity. One of the identity, trigonometry identity is this. So therefore, we found that secant square alpha here is basically 1 plus 2 square, which is equal to 5 here. So therefore, we can put in a 5 here, and then our y will be 3/4 h here. All right. All right. So I hope that is clear at this point. We can try to simplify this as much as possible, but we can leave it here, label it as 1. And then, all right, as you can see, this is our first equation here. We have obtained all the necessary informations that we need. But if you read the question itself, we need to find all the possible value for d in term of h, but we still have an unknown u, which we need to get rid of. Okay, this is where the maximum height come into play, the maximum height of h, right? Okay, now how do we actually find the maximum height in this case, right? By using its trajectory equations. All right, we know that using dy dx. Okay, of course there are many ways to do this in mechanics, but since we have already set up its trajectory equations, might as well we use dy dx in this case. So we're going to differentiate with respect to x. The main reason why I want to use differentiation here is because I want to set up an equations related to h. Okay. Now, if you differentiate that with respect to x, we will get tangent alpha. You get gx u square secant square. All right. And then at maximum height, h, okay, we know that the differentiations must be equal to 0 at y equal to h. We are interested to find out where is this displacement x is when it reached the maximum height. Okay, so we're going to substitute all the informations that we have just now. Now from here you can see that the tangent alpha is 2, so we're going to write a 2 here, and then we have a 5 here just now, so that will be a 5. All right, so 5 gx u square equal to 0 here. All right. So from here we should be able to reach these conclusions. The x should be 2 u square divided by 5g here. All right. Now that is where the x is, okay, when it reached the maximum height here. Okay. Now, once we know this, we're going to resubstitute this one back into its trajectory equations, knowing that the y is h. So here we are going to substitute all this information back. We will get this. We'll get 2u square over 5g. Tangent alpha is 2. Okay, and then this whole thing will be g over 2u square, and then we have the x, which is this, square, and then secant square is a 5, and then this is where we get the maximum height. Okay. So from here, if you try to simplify the whole thing, we should get, let me try to see what do we have here. We have 5, we have a 2, so that is this is 2 over 5. Okay, cool. So we can actually simplify this as, okay, I'm going to write this one down here. We can simplify it as 2u square over 5g here is equal to h. Okay. Or in this case, you can actually write it down as 2u square is actually equal to 5gh. Okay, 5gh. Right. Now the main reason why I write 2u square is because from this equations 1 here, I have a 2u square. So all I need to do is just substitute everything here into this. Right, now I'm going to write it down. So from here I get 2d. From equation 1, I have 2d minus gd square. I have 5 here from here. And then my 2u square is actually 5gh. And then that will be the same as 3 over 4h there. All right. And then it can be further simplified. In this case, you can see that is 2d minus gd square. Okay, I think the g is gone. Hold on, just let me simplify that. So the g is gone. Therefore, you only have d square over h equal to 3/4 h. Yeah. All right. Now that will be our major equations that we're going to solve to find all the possible values of d. Okay, I hope that is clear. Now I'm going to erase the rest here so that we can solve that. Okay, just let me clean this up. We don't need this anymore. We don't need this anymore. Okay, and then here we are. Okay, so from here, I'm going to rewrite these equations one more time. We have 2d okay. And then that's what we have. If you try to simplify that, we will get like 8 HD. You have d square here. Oops, it's not d square, it's 4. There's a 4 there. And then finally you have h square here. And then we're going to rearrange this because our objective is d. So I'm going to arrange this equation so that we can get a quadratic equation in terms of d square. Right. So that would give us d square minus 8hd and then plus 3h square equals 0. Right, now as you can see, we are quite lucky in this case. We can factorize this quite easily. I think it's 3h. And then the other one will be h then. Right, let me erase all this. Okay, so from here, we found that our d must be 3. Oops, let me arrange it in ascending order. So that will be half a h, or d could be 3h over 2 there. All right, and then there you have it. These are all the possible displacement with respect to the origin O there. We solve this using calculus. Of course, some of the students might want to apply the kinematic equations to solve this again. Yeah, you will also reach the same conclusion. But here, I just want to show you the power of calculus, how you can actually apply calculus without actually going through the mechanics kinematic equations again, right? So I hope that this would actually give you a good idea in your next I think it's tomorrow, if I don't if I recall correctly, tomorrow or the next day, your further mechanics exam. Okay, I would like to take this opportunity to wish all my viewers best of luck for those who are actually taking the further mechanics exam in a few days times. All right, best of luck. Okay, I hope all this video has been useful informations in your revisions and in your studies. All right. Okay, thank you very much. Until I see you again.